for one sample test of variances with an example. So this example is 15.1, the darkroom timers. An individual wants to know if the variance for a particular set of darkroom timers is equal or 0.25 seconds. And what they have done was they took like 11 timers from some particular company, and then they set the timings for like 30 seconds and then recorded the time when the actual time while they stopped for 30 seconds. The actual time in the that was recorded as 29.2 seconds. First timer, so it was off by 0.8 seconds, and then the second guys he took like 29.5, so he was off like 5 seconds, 0.8 seconds, were fine, and so on. So those 11 timers, their individual responses or records were the 11 observations. This was, for example, y1, y2, y3, and so on, and we can get those observations sum of y's. We can also get their squares, and we can get their sum of squares for those observations, and that is equal to sum of y is equal to 327.5. Sum of y squares were 9753.15. So we rarely know sigma square or variance, so we estimate it with s square, the sample variance. So we calculate our estimate as s square is equal to, this is the new formula, the machine formula. That's why I was putting these things here, y, sum of y. So let's look at this formula as well. So this s square is equal to sum of y square minus divided by n, and everything divided by minus 1, the degrees of freedom. That's how it goes on. So the calculated s square with this formula, we call it machine formula, is 0.258 seconds, and we want to know whether this 0.258 second is bigger than 0.25 second. If it is significantly greater than that, or we can do it as a two-tailed test, or we can do it as a one tail to the right, and I would prefer doing it as a one tail to the right. And statistical test for one sample test, that's what we are doing. The population under consideration as far as this is concerned is all timers made by this particular company, and sample what we have is these 11 timers, and our sigma square is less than equal to 1 by 4 or 0.25 seconds, and h sigma square is greater than 1 by 4 or 0.25 seconds, and this is one tail to the right. Heaven sample size alpha is 0.05, and x square critical is we can go to a table, or we can go to Excel and pick up the value of chi-square at this alpha 0.05 for the degrees of freedom equal to 11 minus 1, which is equal to 10 degrees of freedom. And we go to the table here, and we are doing it as a one tail on the right, so we pick up this left hand side, then we go for the alpha. Our alpha is 0.05. Our degrees of freedom are equal to 10, so we go in this row. So this is our number, that is 18.31. Same way we can get the same number from chi-square inverse, the function in Microsoft Excel, and we give him 0.95 towards right, and for 10 degrees of freedom, since this gives us the cumulative value coming from that, so we pick we put 0.95 in this arguments of this function, and we get 18.31. There is another function chi-square dot inverse dot rt, right tail. So over there you just put the alpha, and it gives you the value towards right, which is the same as we got now. And then we do the statistical test, the test statistics. Here again we see this machine formula. Let me elaborate the the observations y's, and then this is the sum of y's. Sum are all these numbers, then we take the squares of these numbers and we take the square the sum of squares here, which is 9753.15. Put it into this formula. The machine the sample variance as s square sigma y square minus sigma y and then these the square of this thing, this sum of y's divided by n, and everything divided by n minus 1 degrees of freedom, which is equal to 10. And when we solve it, our number is 0.2581818. And the test statistics we calculate as x square is equal to n minus 1 into s square divided by sigma square, which is equal to 10 into 0.258 divided by 1 by 4, or 0.25. Our number is 10.33. This is the test statistics, or calculated number. And then we compare this number with the critical. This is 10.33, which is less than 18.31. Since we were doing it as a right tail test, in order to reject the null hypothesis, it should have been greater than x square critical. Here it is smaller, so our decision is that we have to reject the null hypothesis. And what we conclude over here is that we fail to reject the null hypothesis and conclude with an alpha which is equal to 0.05. That is the probability of type 1 error, that the population variance of timings of these timers is less than or equal to 0.25. Okay, it is not greater than 0.25, so timers are fine. So maybe we should take